Hi, this is the presentation for the paper Plasticity-Optimized Complementary Network for Unsupervised Continual Learning. My name is Alex and I'm going to present you today. So our main motivation is that the current methods, PFR and Castle, which are exemplar-free methods, are based on regularization. This means that then when they are learning current data, they are trying to return previous representations. But this is giving two consequences. First, there is an implicit handicated plasticity, which means that when you are trying to learn current data, you cannot fully adapt to the data because you have to return previous representations. And the second one is that you have a stability loss when the number of tasks increases because there is few data available per task, and the self-supervision is going to be really imperfect. So there's going to be drifting a lot, and it's going to move a lot your previous representation if you use regularization. As we can see here, we have plasticity and stability plots for a 20 task split of cipher 100. For the plasticity, which is the accuracy in the current task, you can see here in blue PFR is less plastic than our proposed method PFR, and is really going less and less plastic as the number of tasks increase. For stability, we can see the accuracy of task 1, task 8, and task 15 as the number of tasks progresses. And you can see that the accuracy of each task is oscillating a lot, and each time is worse and worse as the number of tasks increases. So our proposed method is based on the complementary learning system theory. We have a main network, green, and an expert network, blue. The main network is going to be responsible for accumulating all the knowledge, and the expert network is going to be responsible just to adapt to the current knowledge. Our method is divided in 3 steps. The first step is to do self-supervised learning in the data using the expert. Here we use Bartlomiej twins, but you can use any self-supervised learning that you want. For the second step, you have to integrate both knowledge, the new learning knowledge of the expert network G, and the previous knowledge accumulated in the main network F. To do this, we propose to minimize the distance between the projected features of the current data and the new learning knowledge G and the previous learning knowledge FT-1. And in a third step, you need to initialize your expert to begin at a good point for the new knowledge. If the architecture of the main F and the expert network G are the same, you can just copy the weights. But if the architectures are different, you can again project the features of the network that is going to be learning to the same dimensionality and then minimize the distance between these two representations. Here we have a few more details of our method. For the second step, you can see that what we are trying to do is minimize the distance between the projected representation of F using the projector N and the projected representation of M again using the projector M. And then you are going to minimize these two distances to try to integrate the new knowledge and the old knowledge in the main network. And for the third step, you can just copy the weights, or if you are doing heterogeneous, again, you are minimizing the distance between the projected features of the new expert and the main network. Here we have results for class incremental learning, but under the homogeneous setup, which means that the architecture of the main and the expert network are the same. We use cipher 100, tiny ImageNet, and ImageNet 100 under 5 different task partitions, 4, 10, 20, 50, and 100 tasks. As you can see in cipher, our method is better for all possible task partitions. For tiny ImageNet, for few task partitions, 4 and 10, Castle is better, but as the number of task partitions increases, our method is better than the others, and the gap is each time going higher between our method and previous ones. And for ImageNet 100, again, for few task partitions, Castle is better, but as the number of task partitions increases, our method is showing that it's better than the other ones. Here we show that if we have a task-free setting, which means that there is not a explicit boundary between tasks, as we can see here, an example, at the beginning we begin to receive data of the blue task, but at some point we begin to mix the data of the blue task with the orange task. And then at some point we only receive data of orange task, but then at some point it begins to mix with the green task data. Here we have a partition for cipher 100 under 10, 20, and 50 tasks. As you can see, there is an oscillation at the beginning, which is getting worse for PFR and fine-tuning when the number of tasks increases. But POCON is always learning, and it doesn't have as much oscillation at the beginning, as you can see. Finally, we show that our method can be extended to the semi-supervised learning setting. Using a few labels provided, in this case the 0.8%, the 5%, and the 25% of the data as label, we show that using POCON with prototypes, we can actually reach very good accuracy. How? So at the end of each task, after we apply POCON, we initialize some prototypes using the learner representations and the labels provided. Then, using those prototypes, we label the unlabeled data and then calibrate those prototypes with these labels, with this sample or these labels we just calculated. Then at the end for evaluation, we just use the distance to the prototypes to predict the class. We call this method prototypes, and to prevent forgetting, we can also have we also implement semantic drift compensation, which it just corrects the drift of the prototype after each class. As we can see here, the comparison against other exemplar-free methods, we are far better than the others. And if we compare against exemplar-based method, the first three ER, ICAR, and GDOOM, we are already better than them in the last task accuracy. But furthermore, if we compare against exemplar-based methods that are used exemplars, 500 exemplars as NNCSL or PAUSE, we are almost reaching the state of the art of semi-supervised learning without using any exemplars. So our conclusion is that we propose a method for exemplar-free, continual and supervised representation learning called POCON, which trains an expert network which is optimized for plasticity. We show doing experiments on Cipher 100, Tiny ImageNet, and ImageNet 100 that our approach outperforms other methods for self-supervised learning, exemplar-free, in continual learning setting, and our method is especially good for many task scenarios. Finally, we show that our method POCON works better than other pure exemplar-free methods in the task-free setting, and it can be easily extended to semi-supervised setting. Thanks a lot.